Let's talk about what we're doing next time we meet. Would anyone like to name the date? 18. Good. That's in 2 weeks. Think of all the things that you could be doing in 2 weeks. And will be. Yes. But I do want you to come to class prepared. Okay? That means you don't have to do anything until the night before, the night of sharing day, if you don't want. But where is our next section? Have we looked in the book to kind of see where we're going here?
I thought we were going to go back to the
Yeah, but we're not going to go there immediately next. We're going to come back. That's actually going to be the last thing we do in this chapter because it really is the hardest. Do you remember what the title of the chapter is?
Light behaves like a particle.
Light behaves like a particle, right? And can we just, to remind ourselves of where we're going, what are the effects of light behaving like a particle? Which one did we already do and complete? And we have not completed the photoelectric effect. I knew you were going to try to trick me into thinking we had and that we didn't have to do this table today, but I'm sorry, no. What did we already do before we even started the photoelectric effect? This is kind of like the history of this course that you've been in. What? Well, frequency shifts were one of the measurements we could do for, what phenomenon are we?
Gravitation.
Okay, so gravity doing what? Gravity affects light, and and we really shouldn't think of it as a redshift, because if we think of the effect as a redshift, redshifts happen to whom? Waves, right? So what should we think of it as? Not a red shift, but a what shift? An energy shift, right? Just like particles as they rise in a gravitational field lose gravitational energy, or gain gravitational energy at the expense of kinetic energy. So gravity affects light, and how many effects did we have? What two? Bending, yes. And energy shift. Okay. All right, so what's the second one? Now is the time for photoelectric effect. Okay, so we have seen so far that the photon theory of light, the lump theory of light, the particle theory of light explains the experiments. And today we're going to see that the wave theory of light does not explain all the experimental results, although it might explain some of them. All right, now, so the goal is now to kind of focus in on, again, the big picture, where are we going when we come back, so we kind of have we leave today with that in our mind. What's the next thing in our chapter? We're eventually going to do the black body curve, but what's next? Compton effect, right? Okay, so that's section 2.5, I believe, right? Okay, so that's what you're going to read for March 18th, which is what day of the week? Which is behaving like what day of the week? Oh, good, you know this. Okay. All right, so of course, I think we meet almost the same time on Mondays as we meet on Thursdays. There's a little difference. Okay, so now I want you to read. All right, we're going to actually spend 2 days on this. For Thursday, read up through Compton effect. See Compton effect on 79? So the first half is really just about what? X-rays, right? And you haven't studied X-rays very much. And it's too bad that we don't have any equipment like many schools do to do X-ray crystallography, because that would be a nice thing to do here. But what you're looking for when you come to class on Thursday to have in your notes is, again, what evidence is this that light's behaving like a particle? And I'll give you a hint, there are two answers. Okay? So there are two behaviors of X-rays that they're going to describe that say, all right, this thing is behaving like a particle. Now, who knows the most about X-rays? Outside of the physics community.
Medical.
Medical people, right? Doctors and dentists. So now you have 2 weeks. This would be a perfect time to do what?
Well, get an X-ray.
No. Although if you need one, go get one. But this would be a perfect time to go to your dentist and get something done so that you could talk to your dentist about X-rays.
I was supposed to come on Tuesday.
Oh, perfect timing! Now, if you're going to have to sit there and, go through this painful, gross, noisy procedure, you might as well be learning something, right? So while he's doing the drilling and the pounding and the poking, ask him how his X-ray machine works, or her.
Sort of hard to talk with.
Yeah.
No, you don't have to talk. You ask the question before, and he or she talks, right? You don't need to talk. If you have questions, what can you do? Write them, right? So bring a pad with you so the dentist can read the questions if you have them. Okay? And usually they'll stop for questions. They let you spit. If you have to spit, go ask your question. Now, people are, the people out there in TV land cannot see the fact that you are all laughing at me. I should have little mirrors here. I'm serious. We need to go to the dentist in the next 2 weeks and find out how their X-ray machines work and if they're anything in common to the stuff that we're reading.
Will they
before.
necessarily know?
All the dentists I have asked have known. That's 3. But they're actually, and they love to talk about this because, if you had a dentist friend, would you want to, and you're going to a party, would you want to hear about what they do and what they find in people's mouths? No. So this is one of the few chances that they get to talk about the work. They love it. All right? This excites them. This is why they became a dentist. Okay? All right, so what is next after we do Compton effect? And Mr. Compton won a Nobel Prize for this. So this is another Nobel experiment we'll get to see. What's next? Is there anything else of light behaving like a wave, a particle, in this chapter? No, there's just what? Going back to the first section. The black body radiation. The black body spectrum. Now, there's a 5th thing, of course, which more of you know. I was really impressed walking around the auditorium yesterday to find out how many students in this class have a seat named after them. At least a majority. Isn't that amazing? These people have more money than you should have for your parents.
My parents were stretching it to get me a seat in the balcony.
Okay. Now, which one do you know about light behaving as a particle before you came to class? And I don't mean today's class, I mean January 5th. What is the most, and you might have not seen it in a physics class, although 2 of you have, although in astrophysics you may have seen it in chemistry class. What's really the first piece of evidence most people experience that light is lumped? Lumpy.
About the emission spectrum.
Yes, we are talking about the emission spectrum, right? Does everybody know what I'm talking about? Those gas discharge tubes. And when you look at the spectrum of one of those gases, what do you see? What kind of spectrum is it? It's a line. It's quantized, right? It's not continuous. And so, really, this is the first one probably everybody knows about. Now, why isn't it in this chapter? Well, because it's so important, it got its own chapter. Chapter 3. Okay? And so, the understanding the Bohr model of the atom and clearly has something to do with light being lumpy too, so it got its own chapter. Now, you might then think that one of these is really remarkable for being on this list. Which? with a list of light behaving like a particle.
Like,
What doesn't belong? Why doesn't this one belong?
Because it should give off a continuous spectrum.
Well, it is a continuous spectrum.
Yeah.
So isn't it remarkable that something continuous, spectrum-wise, is evidence for light behaving like a lump? And you know, for Planck to have done that, I think is just an incredible intellectual achievement to realize that, you know, here is this continuous thing, yet it's evidence for light being lumpy. So, and how he did that is almost all of the rest of chapter 2. In fact, it's so gross that they put most of it where? Have you been looking ahead, like at coming attractions? In the appendix, right? And that's what an appendix is for, right? Things that are so gross they don't want to put them in the regular chapter because they might scare you. Okay, so that's where we're going, and we'll be done with that soon. Now, what's the other thing we need to work on when we come back that you already have possession of?
The photoelectric.
The photoelectric rate. What's the first thing we're going to do? Yeah, plot all our data. Now, again, we have two different stopping voltages, right? For each frequency. So, and frequency number 1, frequency number 2. And why do I have two different stopping voltages? One I'm going to get from where? The direct measurements, right? When I saw the current become 0, what did those numbers read? And of course you're going to have an average, right? And we're going to learn how to do standard deviations and do uncertainties. So I will teach you that when you get back. All right, and the other ones come from the extrapolations, right? So we have extrapolation, all right, we have directly measured, right? And so what we need to do as soon as we get back, and if you want to do this in a special project week, sometimes it can be very demanding because you work 12 hours a day, and some people probably work 6 hours a day. So depending on your project, you might want to start early. I'm going to expect you not to have it done when you come back, but as soon as we get back, maybe by Monday the following, to have all those plotted and extrapolated. Now you're going to have to find out what for each of your curves. You have this curve that looks like this. You're going to have to come up with what? A function, all right? So I'm going to ask you probably on Monday, the 22nd, to bring your algebraic model, okay? And I think, now just remembering from last year's class, there were about 5 different ones, all right? And, you know, people did them independently, and they all worked, or at least they worked for that particular set of data. Now, some people changed theirs after they saw the other people's in the class, okay? So what we're going to do on Monday is I'm going to ask you to pass yours around. We're just going to do like exchange. So they go around the whole room. So you see what other people did and how well their fit was, but you have to come up with a model. And you want to do it on each of your, we're going to do it on each of, say, to begin with, while we're kind of just testing out. But you should do it on at least 3, okay? At least 3 of your curves. Now, should you add your curves together for a given frequency? What do you think? I mean, not add, average.
Yeah.
I would say no. I would say you can average your delta V's after you do the extrapolations. But I think each extrapolation begins with a different set of initial conditions. I mean, when you undid the dial, you may have started a different place and the conditions are slightly different. So I think of each curve as its own data set. Okay, so that, and you want to look at 3 of them at least to do your extrapolation. All right, we need to get on to, and then Adam has a lab to make up, right? That we did yesterday. So maybe the others of you could be collectors. Now, today we need to finish up the boxes here and then hopefully do some other things on the photoelectric effect. So I said I would do one box first. You could tell me which box you would like me to do.
This is for the wave.
This is for light as a wave, right? And we finished light as a particle last time. Yes, Adrian?
I would pick either intensity versus current or work function versus current.
Okay. Anybody want to narrow it down, or
I would rather see
Or-
intensity
or-
versus current.
That's
intensity versus current? Okay. Well, let's use some of what they did in the book. Okay. Did they, in the wave theory of light, say how intensity was related to anything?
So how it's related to energy.
Okay, how is it related to energy, which ultimately is going to be related to what thing here on the board?
current.
So
No, delta.
Well,
velocity.
Well, kinetic energy is going to be related to voltage, right? Okay. Now, in the equations, in the physics that we did earlier this week for light behaving like a particle, are we allowed to keep any of that? Are we allowed to keep any equations from what we did the first 2 days this week? You're supposed to be looking at your equations that we draw in class. I did one of them. Adam did the other. And we use them constantly throughout the week. You're looking at your
Can we
equations.
keep IA times quantum efficiency times E equals current?
You know, current equals intensity times area times quantum efficiency times E. Can we keep that?
No, because that's,
No. Why not?
Oh,
well, then that's treating them.
Right, that was treating I as number of photons per unit area per time. We don't have that concept, right? We cannot use that. All right?
Well, the other one, can we use HF minus the work force or work function or
And the other equation said HF, the energy coming in, equals the work function plus the kinetic energy.
because then you have the
Can we use this? Why not? Where are we treating light as a particle?
where's the work function?
No, I don't think so.
HF.
HF is the energy of what? Of a photon, right? That's the concept that isn't, wave theory. So I thought those were the easy ones. That clearly you can't use these two because photons per area per time is here. Energy per photon is there. If you use the word photon, the stuff can't apply. So is there an answer to my question yet? Are there any physics equations that I could bring
no.
from what we talked about earlier this week?
Well, you can keep conservation of energy.
Well, there's lots of conservation energy. Isn't this conservation energy? It's conservation energy.
Right, but I was talking about just EI equals EF. Keep that.
Well, that concept is okay, but is there another equation here that I used earlier in the week that is still valid? These are not all the equations we've used. There's one more.
Well, we used 1/2 of V squared equals
Just K. Okay. K.
equals EV. But
K
that's
equals E delta V, right? Which was, we got from EI equals EF. This is after the photon released the electron. Kinetic energy plus QVI equals QVF, right? Is this equation still valid?
Yes.
Yes. Right? Because this is only doing what? Stopping the electrons, changing the electrons, kinetic energy to electric potential energy. Right? And that has nothing to do with photons because the photon's already gone by the time we're to this equation. So this was the answer I was hoping for when I asked the question, as opposed to these. But you did always the good educational response, give me the wrong answers first and then the right answer. So they're clapping. Can you hear them out in the teacher line? Okay. So this equation is still valid, but these are not. So we're going to have to come up with a new current equation that somehow relates to intensity. Now, what new equation did they come up with? Can you focus on me, with me? From the reading here, what's the new equation they came up with?
Kmax equals CI.
What page, and what page are we on?
72.
72. It's an
Kmax
equation.
equals CIAT minus.
Okay. And what kind of equation is that? What principle? Where did they get that?
It's through conservation.
It is conservation of energy, right? Although they didn't write it that way. Which is the initial energy?
Kmax equals V.
What? What's the initial energy in CIAT, right? Is the initial energy. Okay? And that, now remember that this time, as I told you earlier in the week, I is now something different. What is I here?
I is
Unit.
Photocurrent.
power per area.
Well, power per area is also what? That's fine, but power per area is
Energy per area.
energy per area per time. And really we should call it flux, but anyway, we can see. So that's very different than the I we had before, which is photons per area per time. And so on your wave box, you know, you got to make it clear that we got a very different thing here than we did before. Okay? So now C is what? Let's use the same symbols. C is the quantum efficiency, right? And so let's call it the same thing we called it before. It says C is the fraction accounting for less than 100% of light absorption. That's exactly what the quantum efficiency is, the fraction of light absorption. Notice that, again, Q, I, and A show up as a product here. And before, where was that product related to? It was related to what? Current. Now, instead, we're relating it to energy, okay, or which is going to be related to voltage. Now, what's the EF energy?
Kmax plus V.
Kmax plus V, right? Which is the same thing we have over here. All right. So, except this time HF gets replaced by an energy thing. Okay. Now, they did something tricky here. What's A?
It's the area of the atom.
Okay, it's the area of an atom. And K then is the kinetic energy of that electron from that atom. Now, are we able to, in a wave concept of light, focus our light on an atom? No, right? So, you know, we understand why this is the equation, but it's not a useful equation for finding current. Now, I suspect one of the reasons you asked me to do this particular box, current versus intensity, is what? Based on the reading. There was no equation that they gave you for current. But I think you could have come up with one. Again, this is conservation of energy for a single electron. This light is flooding many electrons, right? So let's write instead something with the area of what in it? Not the area of an atom, the area of the metal, right? So, and you'll kind of see why they didn't do this. So if I've got area of the metal there, I'm still going to use intensity. I'm still going to have the quantum efficiency because sunlight is still reflected. And I'm still going to have time. What units is that thing on the left? Or what is going to be on the left?
Joules.
It's joules. Right? Okay. Now, instead of all that energy going into one electron, what are we saying goes into?
Entire.
Many electrons. So how do I write that? What do I write on this thing? Kmax plus phi, which is the energy an electron gets. This is not hard.
Over
times
Electron.
the number of electrons released. Right? Okay, where's current? You see current in there somewhere?
Yeah, divided with subject time.
Yeah. Current is charge per time, right? And so, one efficiency, intensity A. We're going to move T to the other side. Okay, now, current is a number of electrons per time. It's charge per time. So what do we have to do to make this all work out?
Multiplied by C.
Multiply by...
By the charge of the electron.
I don't think so. We'll multiply which by charge of the electron?
The number of electrons. Well, before you bring the T over.
Well, but if I've now substituted current here for number of electrons per time,
Oh,
this has a charge in it already now, right?
Yeah.
So I need to do what with
Divided
this?
by the,
I have to divide by the charge on the
Oh,
electron. Okay. And now you see why this is kind of messy, and you can also see why it's not going to agree with the experiment, is we've got current and kinetic energy where? In the same equation, on the same side, opposite the intensity. So it looks like what we are saying here is that if you increase the intensity, what can happen?
You make it goes down.
Well, no, wait a minute. Now, why are you saying that? Kinetics goes down? I don't think so. If I increase the intensity,
Okay.
what could happen?
K makes you go up.
Kx could go up. I could go up. Or they both could go up. Right? So I could get more electrons out. I could get more energetic electrons, or both. And how do you know which happens? What decides? It kind of depends on the really nitty-gritty details of the atoms and how that light wave energy kind of falls. I mean, think of a seashore. Here comes the waves in. That's the light, right? And what are the atoms? The same, right? And so it kind of depends how, that interaction on an atomic scale goes. And so I think we're going to stop here and say, okay, well, it sure looks like if I increases, current increases. Now, is that what we find?
No.
Can I ask you to go back? Can I ask you to go back and look at your what table? Your photon table in your notes, please.
Oh, wait.
What happened? What were the predictions in the photon table? What happened when the current increased? I'm sorry, what did happen when the intensity increased?
The current.
The current increased. There's the equation right here, right? What about here? Same thing, right? So here is a place where the wave people can conceivably say, I'm right. This one experiment by itself does not rule out the photon theory. And in terms of graphs, there's the graph 216a, okay, which says, this is the graph of current versus what frequency versus applied voltage delta V. Okay, and you have one curve that's like this and another curve like that, and those are for two different intensities. And so, if we have twice as much intensity, we also have, which is this is 2I, and this is I. Say, if I have twice as much intensity, I have twice as much current. Everywhere. Okay, so I'm done now. I get to sit for the rest of the class. Well, actually, I hope you can all finish this up in 10 minutes, because, again, I think we have all the equations on the board, right? So, who can do one of the other boxes?
We're not doing time delay.
I think time delay is a really good thing to talk about when we're done, okay?
Okay.
All right, Adrian? Which one are you going to do here?
I'll do frequency versus current. We have our equation for the current terms of the intensity, and frequency is not a factor. None of these are affected by frequency. So,
Okay, I think you should have to do another one because that was so easy. Well, we'll take somebody else next. Everybody agree?
how was that one? I'm not reading.
Where does frequency come into play here in light? What's it doing?
I didn't see
According
it
to the
doing.
wave.
Well, but it's the frequency of the waving, right?
Right. That didn't do anything if it's a wave.
Well, let's think about what the wave is doing to one of these electrons. I mean, it didn't bring this up, but how does the wave cause the electron to gain energy? How does that happen on the atomic scale?
The electric.
What does the light have?
The electric field.
Light has an electric field, right? Electric field is oscillating.
And that makes the electrons oscillate.
Why? What's the connection? Where do we go once we have electric field?
Well, the electrons have a charge, and so
Right.
the electric field exerts a force on
Okay,
them.
what's the force, folks?
Okay.
No.
QE.
QE, right? That's all it is. We got a charge, the electron, we got an electric field, it exerts a force. What about the force? What does the force do as a function of time? It oscillates, right? So, not surprisingly, what's the electron's response? What's its acceleration as a function of time? It oscillates, right? And so it's like the mass on a spring, except there's no spring here. Well, there's a spring that's attaching the electron to the bond to the nucleus. And so, what happens? How should we think of this on the atomic scale? What if you have a force that's oscillating, and this electron is springy, it's a bond again, has a natural frequency, that bond. What happens if you oscillate something that has a natural frequency? You keep oscillating something that has a natural frequency. What does it do? It resonates, exactly. And what does resonate mean? What does that mean about, what does resonate mean in physics language?
Builds up energy.
Yeah, that's true. I want us to go a different way, but that's certainly true. Well, maybe that's actually the same thing, another way of getting the same thing. Building up energy means, how do you build up energy? We had this on the board about a couple days ago.
Increase the amplitude.
Yeah, so you increase the amplitude, right? And isn't that what resonance is? That you've probably had one of those paddle things with a little ball on it and that little string. Do they still have those? Right? If you do it right, what happens to the amplitude of that ball? It gets huge, right? That's a resonance. And what eventually happens? If you're really good at that paddle ball?
All flies on string
It's
breaks.
a string breaks, right? And the electron is released. So that's exactly what's happening on an atomic scale.
That just affects the timing wave, isn't it?
Yes, exactly. So, in some sense, that ought to affect the time delay because the frequency, which is the rate at which you're driving it, if it's high, you might expect the electron to break off sooner, and if it's low, to later. Okay? All right, so we're going to let Adrian take that whole row there, right? The no effect frequency row. Oh, come on now, don't stop whining. Okay, 3 boxes left, and there are 3 people. Okay. All right, and I think, again, these are all fairly straightforward now that we have the equations on board.
It's just as easy to do that.
Well, I know.
Yeah, I'll
We'll let somebody else do
I'll
that.
do that one.
Okay, well, get up and do it.
Well, as you can see from, I guess you want this equation here. If you increase the intensity, well, that'll increase, you're not increasing the number of electrons here. So you have to increase, and phi is a constant, so you have to increase Kmax, and Kmax is E delta V. So If the intensity goes up, then delta V goes up.
And the relationship is, mathematical relationship is linear, okay? All right, now where do we have stuff in the book that we have an experiment that says, yes, this happens, and also let's go back to the photon table. Is this what the photon table predicted?
No.
No, what did the photon table predict?
No effect.
Intensity goes up, no effect. And is there a little graph in the book that says which one of these is right?
216A.
It is 216A, right? They have different intensities. Where's the stopping voltage in the graph? It's that minus Vs thing, right? And that didn't change. So here, as they explained at the top of page 73, here's a place where you don't get for any answer. Okay? All right, we got the 2 5 boxes.
Are we just putting a relationship here or
Yeah.
equation?
Well, we have the equations on the board over there. I mean,
I'll split I can do delta V. Or so here, our stopping voltage is going to be proportional to the Kmax. It's Kmax over Kmax is E times delta V. And it's not a linear relationship here, but as our work increases,
you do K, you do the other column, right?
yeah. As our work
Function.
increases, we've got delta V decreases, and it's going to decrease by the same amount
Yeah.
that the work function was raised.
Okay. All right, now, good. All right, everybody agree? What happened in the photon box?
Same thing.
But not 1 to 1 like that.
Not 1 to 1. Okay. All right, Mike, can you do the last one here?
For this formula, right here, if the work function goes up, then the current can be less to do the same, like, get the same value, I guess, but,
Well, and why is that value on the left staying the same?
because, well, I mean,
If we're keeping the intensity constant,
Right. I mean,
Yeah.
when we talk about one of these boxes, we're only changing the one thing in the box. What are we doing with those other things? Keeping them the same. So what happens?
okay, well, then, if the work function goes up, then the current can decrease.
Okay, and what mathematically?
It's
What kind of relationship is that?
inverse.
Is that what you all would say? Okay, so go tell us the arrows, what goes up is what happens. Is it an inverse relationship?
it's inversely related to Kmax plus the inverse.
Right,
But it's not-
right. So it's not, I think of inverse as when really something, you have 2 variables in y and x, and y goes as 1 over x, not 1 over x plus something. But I don't know what mathematicians.
It's no longer inverse.
Well, I don't know. What do mathematicians do? They say something different in math? I don't know. So it's sort of inverse, but not exactly what I would call it. All right, now what?
Inverse.
Pseudo. Okay, what did the photon box say for that one?
It was independent, right?
Independent, right? Okay, so how many boxes are correct here? And how many boxes are not correct?
2 are correct.
Okay, does everybody agree with Adrian? Which 2, if there are 2?
I don't see 2.
It's the
I
intensity.
believe there are two.
Oh, okay.
Okay, so this one is correct. I believe there's another one that's correct.
And delta V versus V.
Delta V versus V, when it increases, it's not the same.
Yeah, so I would say that's not correct exactly.
It's
So which is?
frequency and current.
I know, I was waiting for this. Get to the answer here. Right? Did we have no effect?
Yeah.
Now, and actually, maybe not as a whole, because we actually, in the photon box, got no current, right? If HF is less than 5.
You don't have that barrier.
Right? So here, we have no effect all the time, but we always get current, right? So that's a big difference. So I would not really even say that box was no. Is that what the photon box said? No. Intensity was what for stopping voltage? For photons. Independent, right? Okay. So current is always about, at least in the photon concept, relating number of photons to number of electrons. Okay. So number of photons related to number of electrons, and the energy was related to frequency. A very clean separation. Do you see that? Number of electrons, number of photons. Energy per photon, energy per electron. Very clean separation. Here, what's happening?
All together.
They're mixed, right? And so they're tangled up, and that's why the results don't match those of the experiment. Okay, we got 7 minutes. I was going to ask you to work a problem, but probably you're not going to be able to work one of these problems in the back. Now, remember what I said the other day when I asked you to read a section? You also read the, and there are a lot here, right? So we need to do some of these when we come back to get back in the spirit of, boy, they have about what? 15. You'll probably want to do at least 10. Okay? What if I asked you to plot a graph of work function versus row of the periodic table? And maybe just the first column, keep the column the same, first column. So in other words, we start with what? Well, we don't usually have hydrogen metals, so.
I read an article from you about hydrogen.
That's nice. It's in Jupiter, which is not a gas. Folks, periodic table.
Right.
Do they still teach that in chemistry?
Yeah, that's
It was last year. Come on, folks, we just have 5 minutes here.
okay. Work function. That's
What's the first atom here we're talking about? What?
Lithium.
Lithium, yes. What's next?
really
No,
No,
we're
sodium.
doing rows.
Oh,
what?
See out there, those people, those alumni that are watching from
Yeah.
15 years ago and 10 and 5 saying, no, we have to do rows and columns. Is it sodium?
Yes.
Well, in the same row as beryllium is lithium is beryllium.
We're
We're
not
going
doing the
down.
same row, we're plotting it versus row.
So we're going down the column.
So we're going down the column. Are we also doing rows and columns?
yes, okay.
Got it.
Is it sodium?
Yes.
Yes.
What's next?
Potassium.
Potassium. What's next?
Rubidium.
Rubidium.
Rubidium. Any more?
Cesium.
Cesium.
Right.
What's that graph look like? Draw the shape for me. What do you think? Now, you don't have much data. You have a little bit of data. Right, on work functions?
Yeah, it's on page 74.
Alas, they don't give you more than one of these. You have to come up with your own shape. What do you think? work function as a function of that. So wait till you all have graphs. And those of you who have one, I'm then going to ask, what is it if we plot what? Phi versus a column number for a given row. How will that go? Let's do this sodium row. What will that be? Sodium? No, that was lithium. Magnesium, right? Aluminum. So I want two graphs. Don't, you may not draw your second set of axes. I know you and your delaying tactics until you have that first graph. I want this one.
That's what I had.
Okay. Okay, so that's your first graph?
Yes.
Okay, fine.
I'll draw my second set of axes now.
Yeah.
Alright.
Okay. Now I don't care, it's hard to know the exact shape. I'm kind of, interested in, does it go up? Does it come down? Does it stay the same? What's going on? Well, what's the consensus here for this graph?
Decreases.
Okay, why would you think it decreases? It does.
Because our atoms are getting bigger, so the electrons are farther away from the charged nucleus, which is pulling them in.
So therefore they feel less force,
They're more likely to
and they're easier to leave, right? So that's exactly right. Okay? So we would expect this. Now, one of the goals here that you want to do in your lab when we come back is to figure out the metal, right? What kind of metal do you think they put in there for a photoelectric effect that is going to work with visible light?
Small work function.
Something with a small work function. Okay. So, now where would you find more work functions? Because this is, I trust you, the metal is not in that table.
CRC.
Right. So they've got work functions more than you want to know. Okay, what's this graph shape look like? All right. Now, how do you know it increases?
So our atomic radius decreases along the
Well, also the ionization energy is.
electron is.
Okay. So we have two ways of looking at it.
And we have.
I didn't know that the atomic radius decreased as we went along the periodic table.
We also have sodium.
And so that would make, using the same kind of argument we made over here, that would make this graph look opposite. But Adrian's answer was one that the way that I thought at first. And what did she say again?
Ionization energy increases.
Yeah, ionization energy increases as you go up. Now, why would that be?
Well, there's
Is it just the atomic radius? Is that the physics of this? Or is
number
it?
of electrons.
That's true. It's easier, always easier to remove one electron when you only have one. Okay. Harder to remove one when you have two. Okay. Now, did anybody actually look at the data? Do we have some data here from the same row?
That's how I got my shape. I looked at
Well, we have sodium and aluminum in the same row, and they doubled, right? Okay. So, and then I think some of the others are from the same row, one of those more complicated, longer rows. Okay. So when we come back, we're going to have visited our dentist and heard about X-rays and read our section, and be ready to plot extrapolate some graphs. Okay.